Alright, so today we're going to be working on related rates. Related rates allow you to take problems where you have two or more variables that are both changing with respect to time and be able to solve them to find information out about one or both of them. So let's say that we had a circle that was increasing in radius by 1 inch per minute. How fast is the area of the circle increasing when the radius is 24 inches? Alright, so we're going to begin by writing the area of a circle, which we all know. The area of a circle is equal to pi r squared. And we're going to start by taking the derivative of both sides. So we're going to go d dt, taking the derivative with respect to time of a is equal to pi r squared d dt. Alright, so taking the derivative, we find we have dA dt, the change of the area over time, is equal to, and we're going to take the derivative of the right side with respect to t. We have our variable r, so we're going to use the general power rule. We're going to bring this 2 down. We're going to have 2 pi r dr dt. Alright, so, funny story, we already know a good chunk of information about this problem, because we know that dr dt has already been given to us. The change of the radius with respect to time, we know, is 1 inch per minute. So we can substitute that back in. And since we know a little bit more information, we're evaluating the area when the radius is equal to 24 inches, we can plug this information in to find the area. So we know that the area of the circle is changing at a rate of 2 pi 24 inches times 1 inch per minute. So we know that the area of the circle is changing at a rate of 48 pi square inches per minute. There we are. Alright, let's try one that's a little more complicated. Alright, so say we have a 16-foot ladder leaning up against the wall, and the top of the ladder is sliding down the building. Oh no! When the top of the ladder is 12 feet from the ground, the ladder is sliding down the wall at 2 feet per second. Pretty slow roller coaster. How fast is the bottom of the ladder moving away from the wall? Alright, so let's start by drawing ourselves a picture, because that'll be a lot easier to see what information we actually know. So we know that we have a building. Let's draw ourselves a little building. There we go. Not too shabby. And we know we have a ladder leaning up against it. There we go. Alright, and we know that ladder is 16 feet tall. And what else do we know? We know that when the top of the ladder is 12 feet from the ground, so we know this distance right here is going to be 12 feet. Then it's moving down the wall at 2 feet per second. Alright, so we know this distance. Let's call this y, and we know this distance. Let's call this x. Alright. So first what we want to do is we want to use our old friend Pythagorean's theorem to figure out what this unknown distance x is. So we know that x is going to be equal to the square root of 16 squared minus 12 squared. And this is going to be approximately equal to 10.58. Alright. Very good. So we know that if we go back to Pythagorean's theorem, 16 squared is going to be equal to distance of x squared plus y squared. And as before, we're going to take the derivatives with respect to x and with respect to y as they're changing in time. All right. So if we take the derivative of both sides with respect to time, 16 squared turns to 0 as it's a constant. And we're going to take the derivative of x with respect to time. So using our general power rule, we know we're going to have 2x dx over dt, the change in x with respect to time, plus 2y dy over dt, the change in y over time. So how far is the bottom of the ladder sliding away from the top of the building with time? All right, so we're looking for how fast x is moving. So we're going to plug in the information that we know so far. So we know that 0 is equal to 2. We know that x right now is a distance of 10.58 feet dx dt plus 2. We know that y right now is a distance of 12 feet. So we can just go ahead and plug in right there. And we know that the top of the ladder is sliding down at a rate of 2 feet per second. So that is the change in y with respect to time. So we can go ahead and plug in 2 feet per second there as well. And you know what? We're going to go ahead and make that a -2 because we're sliding down. We're going to think about this as a little coordinate system. Alright, so now we're just going to do our math. We find that 0 is equal to 21.16 dx dt minus 48. We isolate our variables. We get that 48 is equal to 21.16 dx dt. And if we isolate our dx dt, our change with respect of x with respect to time, we find that, and we're going to move over to the right here, 48 over 21.16 is equal to dx dt. How fast is the bottom of the ladder moving away? And we find that that is about equal to 2.27 feet per second. Alright, so let's say that we had a 6-foot tall person walking away from an 18-foot tall lamppost at a rate of 3 feet per second. Assume the scenario can be modeled with right triangles. At what rate is the length of the person's shadow changing when the person is 12 feet from the lamppost? Alright, so we know we're going to draw some right triangles, so let's go ahead and get those down. So we know we have a lamppost that is 18 feet long. I'm just going to go ahead and draw a triangle here. So we know that this distance right here, this length is 18 feet. We know we have a person that is 6 feet tall, and we know that they are 12 feet away from the lamppost at this distance. So we're going to call this distance x, and then we're going to call this distance, which is unknown to us, y. Alright, so using similar triangles, we know that we have 18 over x plus y is equal to 6 over y. And this is the distance, this is the height of the lamppost as over the combined distance of x and y. We know what x is, but we don't know what y is, but this gives us the triangle is equal to this smaller triangle where the person is standing over the distance y. So if we do a little cross multiplication, we find that we have 18y is equal to 6 times x plus y, which gives us 18y is equal to 6x plus 6y. And we can simplify, so we have 12y is equal to 6x. And since we want to isolate our y in order to take the derivative there, we're going to find that y is equal to 1/2 x. All right, so now that we have our relationship between the rates, the changing rates of x and y, we're going to go ahead and take the derivative of both sides like we've been doing. So we've got y times d dt is equal to 1/2 x d dt. So taking the derivative, neither of our variables are raised to any powers, so we find we just actually have the rate of change y is equal to 1/2 the rate of change of x. And then we plug in the information we know. We know that dx dt is equal to 3 feet per second. So plugging in from there, we know that dy dt is equal to 1/2 times 3, which gives us 3/2. So we know that when the person is 12 feet away from the lamppost, their shadow is going to be changing at a rate of 1.5 feet per second.